Let's look at an example problem where some of the energy is being converted to heat by friction. And so we have a penguin on a snowboard, and so he went down the hill and then coasted to a stop on the flat part. And the first thing we're going to do is figure out how fast the penguin was going at the bottom of the hill. This is a tough problem. Then we'll figure out how far he's going to coast to a stop. That's a little easier. That's more like the homework. And so the initial velocity is given. He's going 10 meters per second. And the height of the hill is 5 meters. And the angle of the hill is 35 degrees. And we're given the coefficient of kinetic friction between the snow and the snowboard. And that's somewhat typical for wet snow maybe. And so the equation, we've been writing the initial energy equals the final, but now that work is being done on the system, we have to take that into account. And so if somebody's doing positive work on the system, they're adding energy, we need to subtract that to keep this in equality. If you go back to Feynman's talk, when Bruce brought over 2 blocks instead of 28 blocks, we ended up with 30. So Bruce did 2 blocks worth of positive work on the system. We'd have to subtract that. Well, in this case, we have negative work being done. And so we're losing energy. We're going to have to add that back. So you might say, why isn't it plus the work? Well, remember, that sort of work is negative. So it's minus negative work. If you just want to add it back in, if you understand what you're doing, that's okay. But this is a more formal approach that handles energy coming into the system or going out. And so initially we have potential energy. We're going to say the height is 0 at the bottom. I think everybody would do that. And we have kinetic. And at the bottom of the hill, we're going to have kinetic energy, and we have to account for the work done by friction as he went down on this incline. And so we have equations for these terms: the potential energy, gravitational potential, mgh, and kinetic 1/2 mv squared. And then the final 1/2 mv squared, and then notice here is where we get minus the negative. And so we're really adding this missing energy back on to keep this in equality. And so the distance would be the slant distance, so we have to do a little bit of calculation to figure that out. If we know the height, which is the opposite of the angle theta, we can figure out that d1 is h over sine theta. And we know h and we know theta, so we know this distance. And so now all we have to do, and this is not easy, is get the force of friction. And to do that, back to a free body diagram. Because we know friction is mu times the normal force, we need to get the normal force. If you think you know it already, that's fine to use it, but let's derive it again as review. And so we draw a free body diagram of the penguin. Normal force is perpendicular to the incline, weight is straight down, and kinetic friction is opposing the motion, so it's parallel to the hill and up it. And we solve the forces in the y, they're equal to 0. And so I have the normal force, and then I have this component of the weight is adjacent, and it's negative. So that's mg cosine theta, and those two add up to 0, so they're equal and opposite. So why did we do that? Well, because of the fun equation, right? Friction, mu kinetic times the normal, so it's mu mg cosine theta. And so again, if you think you just can do that without the free body diagram, that is okay, but I recommend doing this as review, or at least looking over your notes where we've done this before. And so we substitute that in, and notice I put in h over sine theta for d1. We solved for that here. And so you get a little bit of simplification if you want. You get mu, the m goes, and the cosine over sine, you can make that tangent if you want, you don't really have to. And our unknown is the final velocity, and so you could just put your numbers in and figure out what that is. I went ahead and solved for it without numbers, then put the numbers in, and we get 13.56 meters per second. You might see if you can calculate how fast you'd be going without friction, and it's just a little bit faster than this. And so I promised an easier one, and so we're going to move on to that. But again, if you can do one like this, you're doing really well. And so now the snowboarder is the same thing, except we want to know how far is he going to coast. And so we're given that he's going 13.56 at the bottom of the hill. That was the result of our last problem, and everything else is the same. Coefficient of friction is the same. And so what is this distance? And so the initial velocity is given, the heights and theta we don't really need here, but you might use them later, as we'll see. And so again, the initial energy equals the final minus the work. And that's because if you do positive work, you have to subtract it because somebody added energy and it wouldn't be an equality. But if somebody does negative work, you get minus a negative, so it's adding it back in. And so the initial energy is just kinetic. And the final energy as well, there's no kinetic, there's no gravitational potential, there's no elastic potential, there's nothing. And so all we have is this minus work turn. So the work is a change in kinetic energy. You could do it that way as well. And so 1/2 mv initial squared is minus the negative work. So here's where it's important to know that if friction is in this direction and the distance is opposite to that, it's negative work. And if you want another free body diagram, but that's just going to tell us that the normal force equals the weight. And why did we do that? Because friction is mu times the normal force. So mu mg, compare that to the last one where we had a cosine theta. Friction was a little less. And so we can put that in for friction. And in this case, we're solving for d. And I algebraically solve for d. Put in the givens, and we get 93.8 meters. Pretty far, but he was going pretty fast. That's, what is that, almost 30 miles an hour. If you want a challenge, see if you could solve for, this should be D2, without solving for the speed at the bottom of the hill first. And so how would you do that? It'd be similar to what we started with, but you'd also have to add the work in from here and the work from here. So you'd have another term here minus the force of friction that was on the slant times the slant distance that we called D1 before. And so technically D2 there. So give that a try if you can do it, but if you can do one like this, it should help you with the homework. Good luck.